Thank you all. Good afternoon, or good morning, good evening, depending on where you are. So I'll be talking about graphs. Now, the slides here actually and my presentation here is have a slightly different flavor than the rest of the talk. So I think it may be actually beneficial for me to explain where I am and where I come from, so that may give you a better idea about these subjects that I'm talking about here. So I have a very broad interest, and every time when people ask me what I am doing or what I did, the question is actually getting harder and harder to answer. So I figured that maybe it will be actually easier for me to use the word crowd here. So these words are the words from the titles of the papers that I publish. So hopefully you get some ideas about what kind of things interest me, right? So in the middle, there's some learning, some graph here, some networks here, which are actually the subject of this talk. But you can also see data and Gaussian and scalable and model. These kind of things are more statistics and applied statistics, and definitely about matrices. And there is actually a small thing there which is chase of FA, and those kind of things are numerical linear algebra. So, and also some whatever, so random and coarsening, these kind of things. Anyway, so this is roughly saying that I am actually living across multiple fields, some of them coming from traditional scientific computing, and some of them will be more nowadays the buzzwords that everyone's talking about, neural networks and graphs and things like that. So that's about me. And as Tilly mentioned, so I probably is the only one here from the industry. So I come from IBM Research, and particularly the MIT IBM Watson AI Lab. This lab was created roughly 5 years ago, which is really a collaboration model between academia and industry. And our mission is to actually, we have two important things that go at the same time. One thing is that we do AI, do research, and keep publishing at the top conferences. So those are the research parts that I'm sharing with all of you here. The other side is really we try to do all the things that actually benefits the society, benefit IBM, bring revenue for IBM. And so this is the business side, and it is just basically saying that, so the projects that we are conducting are very much application oriented, and a lot of times the very first question we ask about why do this project is where's the impact and who cares and things like that. Anyway, so this is something about me and about the place I work at. So I'll be starting with graphs, and these are particular examples that we are looking at. When we talk about graphs, there could be large graphs or there could be smaller graphs. The large ones, for example, the power grid, right? So this is the power system of the entire United States. Those power lines connects the power stations, substations, or every families. So this very naturally form a very large scale graph. In the middle, there's a social network. Right? So these are, if you just think about Twitter or Facebook, you have user accounts, and then people follow each other or be friends with each other. So we have these pairwise connections. So that also forms a graph. We also look at financial transactions, and in one particular work that we did, we actually look at cryptocurrency, Bitcoin there. So every node here in this graph is actually one Bitcoin transaction. And the special thing about our Bitcoin is that when you have some money at your hand, then you'll be spending this, and then so all the edges going out have to sum the same as the incoming edges, right? So you gain the money from incoming, and you spend the money outside, and then so these are some special things about the Bitcoin network. So these are graphs, and they can go to very large. So 1 billion nodes or 10 billion edges and things like that. On the other hand, we also care about graphs that are small, right? So molecules are small graphs, and especially if you just think about some drug-like molecules, it could be like having a dozen or 2 dozen atoms and having bonds connecting them. Or if we do programming, right? So if you look at a small piece of code, it can actually also be turned into a graph by looking at the path structure, and also look at data flow and control flow. and various different things. So in real world, there are a lot of scenarios about graphs, and that is one of the reasons why nowadays when people do machine learning and deep learning, they very much interested in looking into graphs and see how models can be built for that, and how we can do a better job for predicting things and forecasting things. So whenever I'm talking about graphs, I always have the sparse, I always have the matrix in mind, and that's what really intrigued me. I think it's very fascinating, and actually, I thank Yusuf very much for bringing me into this world. So if you, so I show an example graph here, and whenever I look at a graph, I look at a graph adjacency matrix. And whenever I look at a sparse matrix, I try to understand if there is actually a graph, an underlying graph behind it. So actually, this is two-way. And again, I mean, so this matrix is super sparse, right? So and a lot of times, actually, when I draw matrices, I deliberately leave out a zero because that reminds us not to store the zeros. Of course, there are a lot of interesting things we can do for graphs, and there is a matrix language for that. And I think Tim Davis has been mentioning about that for an entire hour yesterday. So for example, I mean, so we do reordering, we permute the rows and the columns of the matrix. That is often done when we are doing sparse Gaussian elimination and things like that. So one example here is that the graph here is special. It is not a general graph. It is actually an acyclic graph. So for an acyclic graph, you can actually do a sorting, where you sort the nodes of the graph, and so that the edges are always coming from the small indices to the large indices. You never have an edge that go back from large to small. So what that means is that the adjacency matrix after such permutation, it is triangular, right? So the lower triangular part is entirely empty. So these are just one small example of trying to connect graphs with matrices. And sometimes if you're so oriented towards matrices, then maybe you can actually find something interesting from the graph angle, and vice versa. Anyway, so again, I mean, so the different flavor of my talk from the rest of the talk is that I'm actually injecting a lot of machine learning here. So in order for everyone to be on the same page, so I'll just give you a one slide introduction of what machine learning is and what exactly we are doing. So an example is on the top right corner here, right? So we have an image, and we try to figure out what is the object in the image. All right, so what kind of mushroom is this? We have three choices, and then we have to figure out by using a neural network or by using whatever function just to figure out which answer do we pick. Right, so eventually we are generating a probability vector. All those just give a score for every answer, and all the scores sum up to 1, and then we pick the highest score. That is the answer we pick. So mathematically, so this entire thing actually have three components here, right? So one thing is when we talk about the model, which is the function mapping itself, that takes input and provides an output. The other thing is about the loss, because because we need to do the third thing, training, right? So the training is really, we set up some loss function and minimize the loss when we compare our prediction with the ground truth. So these are the major components of machine learning. So when we talk about the model, I'm using a notation f of x theta. So x itself is the input. It could be anything, either just a column vector or could be something more complicated. So the f itself is the function mapping that gives you the output. And in this particular example, we give you 3 output numbers. They sum up to 1. But really, one of the most important things is about the theta here. So theta is the parameter of the function, which is the things that you have to learn. So that learn is, so the machine learning really comes from the learning of the theta here, right? So it's just like, if you don't think about very complicated neural networks, if you just think about fitting a line, so there's linear regression, right? So we have some data which is roughly on the line, then we'll want to find a line, right? So what exactly does it mean by finding a line? So that means we need to find the intercept, we need to find the slope, right? So those are the parameters. Now, when we make the model more and more complicated, the parameters, I'll just summarize that as a theta, and then I'll give you one particular example of what that is. So that example is actually exactly here, right? So I give it a specific form of that function mapping here, right? So there is an input X, there are some matrix W, there's some vector B here, and so there is some function, whatever, and eventually an input X, an input vector X, and an output vector F. And the theta is summarizing all the things that we want them to be there. We don't know what exactly the values are. We'll be using the data to drive us, make a good guess of those values. So in this example, there are some nonlinear things here going on. Otherwise, everything will be just linear, and then we're actually just doing linear regression. So what causes the nonlinearity is that in the middle there's a function which is called ReLU. ReLU is actually just saying that, I mean, so if the input value is smaller than 0, then I'll replace that by 0. Otherwise, I'll just keep that value. And we also have the softmax. The softmax is acting on a vector. And then what happens is that we'll be first raising an exponential for every entry of the vector, and then normalize them in order such that they sum up to 1. So that is the mechanism for us to produce a probability vector, right? So everything is positive and they sum up to 1. So that's the model. That's something that we'll be using whenever we have new data X. But really the question is that how do we figure out the unknown parts of the model, right? How do we figure out the theta or the W's and the B's here? So the way of doing that is, first of all, we have to figure out, we'll have to establish a loss function. The loss function says that I really want my prediction F to be close to the actual ground truth Y here, right? So if my output Y, if my F is producing a vector of length 3, then I actually have a ground truth label, which is Y, and Y is also a vector of length 3. Some of the entry, actually one particular entry is 1 and the rest of them are 0. So that one particular entry says that, hey, it is really this candidate rather than the other candidates. And then we're looking at all of them entry by entry and then compute this so-called the cross entropy loss. And then sum up all the entries and there is the loss. All right, so this yi here is the labeling vector. It is a vector and it has one single one and all the rest of the 0. So, and there is the ground truth. It tells us what mushroom is that. All right, so so the training part is getting to the optimization, right? So that again, I mean, so everything here, even though we are using the language of machine learning to talk about things, at the end of the day, it's just doing numerical optimization. So there are many ways to optimize such a thing in order to find the best theta here. The standard way, or 100% of the people in the field using, is stochastic gradient descent. So what it means is that so rather than looking at the entire loss function L here, we'll be looking at the loss function that is computed by using only a small batch of the data, right? So I'm indexing my data by using I here, and then I'm saying that I take a small batch of the data I from some set notation B that I'm using, and then I sum them up, and then I use that to compute my gradient. And on the right, you see that I've computed a gradient, and then scale that by gamma, and then subtract it, and there is a way for me to update the parameter theta, starting from some initial guess theta 0 and do, I don't know, maybe it's 10,000 iterations or 100,000 iterations to get to the final theta which is the model parameter. So this is the basic machine learning thing. So now it comes to the graph to the graph case, right? So what is the same with the rest of the data kinds, and what is different, right? So so the same thing is that, I mean, so we always talk about X and Y, right? So X is input, d-dimensional, and output is a probability vector, right? So we always need something that sum up to 1 and positive. So that is the same thing. And the task is also the same, right? So we have a bunch of data points. Some of them here are known. We know the label of them. We know the Y value there. Those are the purple nodes here. And then some of them, we have to figure out what their predictions is. And I'm using an example of every data point here is actually one paper, right? So so paper number C is something that I know, hey, that paper is about theory. If I have multiple choices about trying to predict what that paper is about, right? So, and then there are some, for example, for paper D, I have to guess what it's about. Is it about theory? Is it about neural networks? Or is it about reinforcement learning? So I have to make a choice. So that is my task, that is my job. So I have to do a job to figure out the function f that fits very well about these purple nodes, and hopefully also can also do a good job for the yellow nodes whose labels that I really want to figure out. So this is the same with the rest of the world in machine learning. But something special about graph is that the data points are not independent, they are actually connected. We have edges here, right? So some paper is connected to another paper because one cites the other, or because both papers are written by the same author, or because of whatever, right? So you have the graph and you have these connections between the data points, and this just gives us some extra information to figure out their function f, to figure out those parameters theta, and that's it. So that is one particular use of graphs, and there are actually a lot more innovative use of graphs. In that case, we just try to figure out inside the graph what each individual node is about. But now we could also figure out what each individual graph is about. So in this particular case, I'm actually showing some graphs, and some of the graphs are about enzymes, and some of the graphs are non-enzymes. And then I have question marks for a lot of other graphs that we don't know whether they are enzymes or not. So our job is to say, hey, my input is just a graph, and then let's figure out what is the label of that. Let's just give a probability. I mean, so maybe 0.95 probability is enzyme, and 0.05 probability it is non-enzyme, and that's my prediction. Yet there are a lot more other scenarios. So there is also a time series scenarios for that. So if you look at the time series, it is just a bunch of numbers in a row, right? So and of course, I mean, so they are ordered according to time. So maybe we already know some values in the earlier times, and then our job is actually to predict what's going on in the following time steps. So if you think about time series, and now I'm splitting these into x and y, right? So the left part here is some I know about the values or at that time, and the y part is the part that I want to predict. So this and this is one particular time series. If we have a lot of them, and some time series is connected to another one, in that case, we do have a graph behind. We do have a graph of the different time series. So in that scenario, then the things that I'm talking about also applies. So, all right, so now after the motivation, I really want to start into looking into the details here, right? So the specific function f here, I'll be using this very particular function here. So they call this a graph convolution neural network. And this is one example of the thousands of graph neural networks proposed in the past few years. And the reason why I put this mathematical form here is that maybe you are more oriented at reading matrices. So I just put things in a matrix form, right? So now you see A here. So A is the Jesus matrix, it's n by n. So that means we have n nodes. So the x is input. It is not just one single node anymore. I'm actually putting all the n different nodes and different inputs together, one per row, and formulate that as a matrix. And again, we have some parameters W here, and also some nonlinear function, which we call activation here, which is the ReLU. And we also do a few layers because we will be using the matrix A multiple times. And then eventually we get the prediction, right? So this prediction, this F here, I am not just outputting a probability vector for one particular input. So I'm actually outputting a probability vector for all inputs, right? So for all inputs together simultaneously. So that's it, right? So if you tell people that, hey, I want to, or if you tell me that, hey, I want to work on graph neural network, and all right, so look at this map and try to figure out how to get the W, and that's it. So, well, I mean, so this conference is about numerical linear algebra, right? So we can also look at this from the matrix angle, right? So when we look at particularly the one layer of the neural network, right? So there is an A multiplied with an X and multiplied with a W, right? So if we draw all these matrices here, what do we see, right? So if we want one particular row of the output, that is actually a linear combination of some of the rows, and that linear combination is entirely determined by the adjacency structure of the graph, and possibly with some weight. So now I'm really trying to use the language in machine learning. I mean, so we are actually calling this as aggregation, because whenever I want to get something for a particular row, I look at actually the rows corresponding to the neighbors of that particular node, right? So I'll be aggregating information from my neighbor. And you could immediately imagine that this is just one single layer. So I'll just aggregating my one hot neighbor. But when I go to another layer, then I'll have to go to the second hot neighbor and more neighbors. So the GCN, the graph convolution network, is just one particular example of the function F. And in the past years, as I mentioned, there are actually maybe 1,000 or maybe even 10,000 other designs of this function F here. And I'll be just summarizing a lot of them in this abstract form here, right? So whenever I want to get something for the node I here, HI, of course, I look at it HI, but in the past, information, so superscript L here indicates the layer and also indicates whether it's done in the past or in the current. And besides that, I look at all my neighbors. So those J here, J belongs to the neighborhood of I. I'll be actually doing some aggregation of them. So this AGG is actually a very abstract operator, right? So in the GCN case, it is just using the matrix weights to do a linear combination, but there could be more and more innovative design. And here are some examples, right? So if we look at a graph stage model, we are saying that, hey, there is actually there is still just some linear combination, but maybe, for example, if you look at the GAT, the graph rotation network, right? So the I itself is still I. We have the HI there. And then the J there, those J's are I's neighbor. We have a summation over all the neighbors of I. But the thing is that the coefficient in front of them, those AII and AIJ there, they are not just the matrix weights. They are actually computed by something very complicated here, there, right? So those things depend on the age that are computed in the past. They depend on additional parameters, W. There's also a lot of nonlinearity. There is some exponential and some normalization. So now it really becomes nonlinear, right? Because these alphas are not constants anymore. All right, so these are some examples of what the function F here, what the function F is. So starting from the, I'm actually already done with the introduction of graph neural networks. But a lot of cases, I mean, so when I'm trying to look at something, I always just ask myself at the beginning, I mean, so what is this or what is that, and what can I do about that? So immediately you can see a lot of questions. All right, so why do these kind of models work? Why can I use this ELF and I can get 100% prediction accuracy, right? So, so if I have these kind of models and does it scale to a graph that is super large? What happens if that A matrix there is actually changing over time, right? So it is not just a single A matrix there, it is actually having a subscript T, and we have A1 and A2 and so on and so forth. It changes over time. And what happens if I change the graph structure a little bit, right? So I just erase one of the non-zeros in the adjacency matrix A, then would my model be entirely different? Would my predictions be entirely different? Right. And if I look at some graphs that are very special, not a general graph, for example, if I look at a acyclic graph, is it possible for us to actually define a better function F there, a better model to deal, because we know more structure about the graph, right? I mean, so the edges don't go back, right? So maybe we can design some better model to capture that. What are the other questions? Yeah, actually, some of these questions are easier than others, and some of these questions are more mathematical than the others. And so the sixth question here is actually more mathematical, right? So if we think about, let's say the weight matrix W here, I mean, so I can actually make the weight matrix W to be infinitely large. The number of columns can be infinitely many. What happens? I mean, so is there any asymptotics there? Is there any limits there? Can we prove any convergence, whatever? So, or if we talk about neural networks, right? I mean, so we can run it 1 layer, 2 layer, 3 layer, whatever. I mean, so what happens if I run it infinitely? I mean, so if I run it using infinite number of layers, do we see any asymptotics or any convergence or any limiting behavior, whatever? So these are also limited, legitimate questions to ask when we consider graph neural networks. The seventh question is actually one of my favorite, right? So whenever we talk about these models, it's because we are already having a graph. But what happens if we don't have a graph? Now, in the past lecture, Yusuf mentioned that, hey, you can generate a KNN graph, that's fine, but maybe there are actually also more ways to generate a better graph that can fit the data, right? So, and the eighth question is actually something that we are actively investigating, right? So if I already know some graphs, like some molecules, can we actually learn from that, learn those patterns from there and generate more molecules? So that is about generating new graphs. So all these are surrounding graph and graph neural networks. And if we go back to the very first question, I mean, so why do graph neural networks work? I mean, so a lot of people try to understand and do analysis with that. But to me, it's really from a statistical point of view, there is actually one very famous saying which says that all models are wrong. So it is probably not a good idea to trying to do a lot of mathematical justification why this model or not that model, but it turns out that some of them are more useful than others, and it fits data better, it fits our intuition better, and so on and so forth. So anyway, so I'm actually posting a lot of questions. I'm not going to answer them. I'll just pick 1 or 2 of them and give you an idea about the specific work that we do along that direction. So the first topic is about learning with massive graphs, right? So if I want to deal with a graph that that has 1 billion nodes and 10 billion edges, can I still use my laptop, or do I need to use a supercomputer or whatever, right? So how can we deal with the case of very large graphs? And in each of these topics, I'll be listing 1 or 2 papers that we wrote for the topic. So for this particular topic, let's try to record a setting, right? So we have n nodes in the graph, and then for each node we have a feature vector. I'm using that input vector x as the notation there, as you recall, right? So they are d-dimensional, and then the output will be c-dimensional because I'm actually picking choices out of C candidates, right? So mathematically, I'm actually trying to find a model F that maps x to y. My x is n by d, y is n by c, and of course I have a matrix n by n there. And then I'll be focusing on one particular model there because I have the mathematical notation there. It will be easier to understand, but really the methods that we developed there is actually applicable to a majority of the graph neural networks. Right, so now the question is that how can we find the parameters of F, right? So how can we find this W0 and W1 efficiency when the matrix size n is large? So this is something very unique for the graph case, very different from images or text or sound waves. We have the problem of neighborhood explosion, as I recall it. If you recall me, so when we do the training, every time we pick a batch of data, so that means we pick a small number of nodes, and then try to compute that the F of those nodes. So suppose that we want to compute the F of the node A here, right? So now I need information from its neighbors, which are the purple things, because we have a matrix multiplier there. But then when we look at how can we get information for the purple nodes, for example, the B node here, it needs actually information from its neighbors again, right? So those are the inner A that that we use to do the computation, right? So all of a sudden you see that whenever I want to compute something for one single data point, very quickly I have to use entire data sets, because when we get neighbors, it is even just 1 or 2 hops away. It could be actually very easy to get into the entire graph. In the past, when people do social network analysis, they have the theory of 6 degrees of separation, right? So if you make friends and your friends make friends, and eventually just going 6 hops away, then you know everyone in the world. That is more or less what happens for the graph. So this is highly inefficient, and if you want to do this also on accelerators like GPUs, I mean, you just cannot fit everything inside the GPU. So you have to squeeze your neighborhood. You have to make it smaller. So one thing that we propose, which is very simple, is that let's just sample our neighbors, right? So when we look at the first of neighbors, those purple there, I say that I only pick 3 of them, even though there can be many purples. And whenever we go to the second hot neighbors, and even though there are many yellows, I'll just pick 4. So I always say that I pick a constant number of neighbors every time when I do one layer computation. Now, so mathematically, that is just saying that whenever I do computation with the node A in the middle, everything is constant. It is all 1, right? So, actually, this very simple thing works terribly well. Of course, I mean, so you all ask why does it work, right? So, and this is the summary, right? So we actually do have a theorem of showing that if we do this, then actually we still can run the optimization, and the optimizer can go to the optimal theta. So the idea about that is because we are doing sampling, and even though because of the nonlinearity in the middle layers and outside layers, doing the sampling would not maintain the unbiasedness of the estimate of the gradient estimates, but it is still consistent. Consistent is actually, so consistent estimator is actually just means something like the probability bound in the 3rd item there, right? So whenever I have the ground truth, which is the gradient there, I have my estimate, which is called GK, and then my estimate differed from the actual ground truth gradient by a difference delta, and that probability would goes to 0 for any delta. And as long as that happens, then that means that my gradient estimate GK is consistent. And of course, I mean, so we can assume a lot of things like how fast does it go to 0. So now here I'm saying that it goes exponentially fast. So the NK here is roughly speaking the number of neighbors that I pick. So if I pick more and more neighbors, eventually the probability converges to 0. Right? So I'm making these assumptions, and together with other assumptions in the usual literature of stochastic optimization, and eventually we prove a bound like that. So what does that mean? So the capital T here means that I'll be doing my training. I'll be doing my gradient updates T times, and I prefix that. So if I do that, I look at the gradient at theta k, and look at the squared norm, and I take the minimum of them when I over the entire course of the optimization. So the smallest of that gradient norm squared is bounded by something on the right. So there are some constants there, including the delta and the L and the G and whatever. But the important thing here really is in the denominator, there is a square root of T there. So roughly speaking, this is basically telling us that the error would decay something like 1 over square root of T. And now, yeah, it's just pick T that is large enough, like 10,000 or 100,000, and eventually you'll be satisfied that the gradient is close enough to 0. And then you conclude that, hey, maybe this is the theta that I want. So yeah, I mean, so for interest time, I have to just present it like this. I mean, actually, there are a lot of experiment results telling you that, hey, we get actually a factor of 100 times speed up when we do the sampling and do the chaining and things like that. And we don't compromise any accuracy, any prediction accuracy, and so on and so forth. But I'll skip that because I do want to give you more flavors of other projects that we also worked on under this umbrella. But if you do have any questions, just stop me anytime. I'll be happy to take any questions. So, okay, so the second topic that I want to talk about is the case when a graph changes over time, right? So now it is not just a single A there. So A has a subscript T, and T goes from 1 to 2 to infinity. So what kind of model can we build for that? That's the question there, right? So, so when we are talking about graph changes, it is actually not just some edges coming in and some edges going out. Actually, maybe some nodes were also coming in and some nodes going out, right? So the graph size actually also changes. So again, I mean, so mathematically, if I have at time t, if I have my input data xt and have my label output data yt, then I still want to figure out a function f that maps xt to yt. And it is just that I want this f to work for all t from 1 to infinity. So this question is really more about modeling, right? I mean, so very naively, we can just try to use the previous model, right? So now I'm just having more x and more y, and then let's try to train a model, and that's enough. But really what we are not satisfied with is that the model will not change over time, but we do want to make it change over time. So if we look at the model, I mean, so that so I'll just recap the formulas here at the top right corner. The entire model is at the top, and then if we look at each individual layer, then what happens is that I'll be using my H. So the HL is something that will be changing over the layers. Initially, it is the input X, and after a few times, eventually we get to H of some capital L or something like that. And right, so everything here does not have a subscript T, but now I'm saying that my A has a subscript T. So my H definitely, of course, also have a subscript T, right? But is there enough? No, there's not enough. So what we are proposing here is really, we also put a subscript T there for W, right? So the W is the parameters that I want to estimate for each time step. It changes over different time step. So the way of doing that is we'll be just actually injecting some recurrence here, right? So what I'm saying here is that my W is actually not something that we need to figure out anymore. W is actually a function of something that we will try to figure out. So the W's here, although they are the parameters of the original GCN, they are actually now not the parameters that for this particular model. They actually depends on some other parameters. So there are two ways of changing those W recurrently, right? So here I say there is an H version, there's an O version, and really at the end of the day, I'm actually just trying to use recurrent neural network to update that W, right? So the W is no longer something that I learn at every different time step. It is actually, there is an underlying recurrent mechanism to control how my model parameters W will change. There are obviously two ways of doing that. If you have certain familiarity with with recurrent neural network. So when we talk about recurrent neural network, the network itself actually maintains a state, and then every time when you inject some information into the system, which we call the input, the state would change. So now in this particular case, the W could either be the input or the state. Right, so at the top, at H version here, I'm saying that I'm treating this W as the state, right? So my H is the input. So every time that I inject my H into the recurrent system, then it changes the W. So there is the H version that we are proposing. The O version says that no, oh, sorry, actually that is the O version, sorry about that. I mean, so the H version is saying that actually the W is the system state, right? So I get my input H there and the system state changes. The O version says that my W is actually just the system input. And because of the recurrence, input becomes output becomes the input of the next time step. So anyway, I mean, so this is actually very abstract, and I don't know if I'm actually not intending for you to digest all the math here, but it is just to say that, I mean, so there is actually a way for us to establish something that is going recurrently, like a Kalman filter or dynamical system. When we talk about things that changes over time, then we're actually exactly injecting that kind of mindset into a graph neural network so that it can deal with the case where the graph changes over time. So again, I mean, so does it work? I mean, so these are the typical tables that we usually put in the papers when we develop a new model or propose some methods, right? So every column here is one data set, and every row here is one method. And the proposed method is at the top, is at the bottom, and then we're actually comparing with a lot of baseline methods at the top, and then eventually we just show that, hey, our method is actually doing the prediction more accurately by having a smaller prediction error or something like that. So in this particular case, unfortunately, the proposed model here, which we call the evolved GCM, both H version and O version, they are not always the best. So for some data set, for some columns here, one of them is the best, but for some other data sets, they are not. This is actually something that I'm not entirely satisfied with, and I'm actually open to a lot of innovative ideas of how we can actually inject the dynamic or the recurrence mechanism into the system more accurately, so that it can perform the job better. For people who are actually solving ODEs in time or doing dynamical systems or doing Kalman filtering or things like that, I welcome a lot of feedback from you to teach me if ever we can actually improve the model. So this is the third subject, which is one of my favorites. It's about learning the graph structure. As I mentioned, right? So if we have some data, we can get a graph by constructing a KNN graph, but we can actually do a lot more than that. And the actual use case is that we look at the entire power system of the United States. There are thousands of sensors installed at some of the power stations there, and they're actually monitoring the state condition, the condition of the grid, right? So they're measuring the current, measuring the voltage in real time, 30 times per second. And then so we'll be using those data and try to figure out if at some point something wrong happens in the grid. So unfortunately, we get only the data about a time series. We get a sensor reading, but we actually don't get we don't get the grid topology, right? So you can imagine, I mean, so that's national security. I mean, so the power grid cannot be disclosed to anyone. So now the question really is that we have data here, right? So at every sensor, every substation here, we have, like at station A, we have some time series, and at station B, we have another time series. So the question for us is that if we have this data, can we predict what's going on in the next seconds, next minutes, next hour, next day, next week, and so on and so forth? And also, maybe at some particular time step, some of the sensors are actually malfunctioning, and because of whatever reason. So if you just visualize these time series here, right? So some of them are actually behaving normally, like B and C and E, but some of them have big fluctuations like E and D. So the job there is to figure out, hey, I really want to predict that A and D is actually doing a bad job here. There may be something wrong. There may be a failure or something happening there. So I want to predict that. I want to predict that in real time, and want to predict that really fast so that grid operators can respond quickly. So these questions, again, I mean, so we have data, we know that this data come from a graph, but we just don't have the graph. What can we do? Now, there are two ways to construct a graph, just besides the KNN, right? So one single way is to do a link prediction, right? So if we have certain representation of each individual nodes there, then we can make the inner product and do some squashing into 0 and 1. So that gives us some probability of the existence of an edge between two nodes. So this is something that is actually very common in the machine learning literature, right? So I'm showing here at the very beginning, we have some time series here. I mean, so at each time step, we have a short vector here. There is an entry about the voltage, an entry about the current, and so on and so forth. Then we can summarize each time series denoted by one particular color here into just one single vector here with the same color. So that is what I call as a feature extractor here. So I'll be using just a vector of dimension, maybe 10 or 20, whatever it doesn't matter, to summarize the entire time series. And once we have that, then we'll be building a link predictor, right? So a link predictor says that I'll be using the yellow vector and also the blue vector together, maybe take the inner product and then compute a sigmoid transform. That would give us a zero, some number between 0 and 1. So there is the probability of, so that tells us what is the probability of having an edge between the yellow and the green. And that can give us the graph. So there are, of course, I mean, so there are some parameters inside there. I mean, so in my feature structure, when I try to summarize the entire time series into a 20-dimensional vector, there are some parameters. So those are parameters that I need to learn about. I need to find the optimal ones. Once we get that, then we say that, hey, the graph we get from here is optimal according to whatever criterion that we impose. So this is one way to construct a graph inside other pipeline of doing predictions or forecasting. Another approach, which is actually has a stronger mathematical flavor, comes from probabilistic graphical models in statistics. So in that case, we are looking specific. We are actually requiring that a graph cannot be any graph. It has to be directed and acyclic. So the acyclic, again, I mean, so it just says that we don't, there's no any loop, right? So and such a graph is actually such kind of graph is actually the fundamental form in probabilistic graphical models for us to infer, for us to do inference. So, and what it means is that it could factorize the distribution into much simpler conditional distributions so that we can compute the probability there. So for example, here I have a graph with 7 nodes. And then if we treat each particular node as a random variable, then we have a joint distribution among 7 random variables. And in order to, to compute this probability from whatever probability model is actually a terribly hard job. But using a directed acyclic graph, it actually allows us to say that, hey, I just pretend that this joint distribution can be factorized into the product of 7 simpler conditional probabilities, right? So then this condition says that, so this condition uses the graph structure. Like for example, if we look at the probability of node E, then it does not depend on everything else. It depends on only C and G, because there is an edge from C to E and also an edge from G to E, but no other edges going into E, and so on and so forth, right? So this is the way for us to come out with simpler probabilities to summarize an entire probability distribution. And we can actually generalize that for the time for the temporal case when we add an additional dimension, add an additional temporal dimension there, right? So I add more copies of the graph. Every copy is for one particular time step. And then again, we're just using edges to connecting them. And so whenever I'm trying to compute the probability of observing this entire thing, now I don't need to figure out how to do that. I'll just need to look at the individual conditional probabilities there. So now our modeling job is really to figure out how do we model those conditional probabilities and then chain them and then fit them by getting the best likelihood. But again, I mean, so the most important thing here is that suppose we have a graph, suppose we have a acyclic directed graph, we can factorize a probability distribution with respect to both time and nodes, right? So these A, B, C, and D are nodes, and 1, 2, and 3 are time, into very small probabilities, conditional probabilities, right? So the probability is conditioned on some other nodes, like we have B1 condition on A1, right? So B condition on A, but not other nodes. But also when we look at time step 2, right? So B2, B at time step 2 condition is conditioned on A at time step 2 and B on time step 1, and not other nodes and other time steps, right? So this is the entire machinery for us to write down how do we compute the probabilities, and then we try to infer the graph that will maximize this probability. So that graph is the graph we want. That graph tells us that, hey, really, node A, maybe node B really just depends on A, but not depends on other things. So sensor B or substation B, if we see that there's some events happening, if there is a failure happening, maybe it is caused by some substation A somewhere close, but not other substations. All right, anyway, so again, I mean, so you'll see a lot of such tables in machine learning papers. I mean, so you're just comparing with a bunch of methods. Some of them are not using deep learning. Some of them are using deep learning, but no graph. And some of them are using deep learning, but with graph, so on and so forth. And then at the very right, we also put our method there, and then to show that our method is actually forecasting better and also predicting better than all of the existing methods. All right, anyway, so I just gave you 3 example ideas of what deep learning is about and what graph deep learning is about. So there are actually a lot more. So of course, I mean, sorry, if you're interested, just go to my homepage, and there are tons of papers there, and each one has some flavor there, and just pick one of the things that you're interested in and do some further reading. So if you're interested in how to train neural networks with graphs that has 1 billion nodes and edges, then look at efficient training, right? So if you are interested in, for a case when a graph changes over time, look at dynamic graphs. If you want to try to figure out how a graph can be constructed besides KNN, do the structural learning. And there's also some graph generation thing, coarsening thing, and application things going on. So one very peculiar thing about our lab, going back actually to our lab, is that we actually do a lot of applications, right? So whatever is state-of-the-art models that we are proposing or new methods that we are proposing, we want to make sure that they're actually used somewhere. And so some of those applications would be for finance, and some of them would be for climate or whatever. All right, so I think this is actually my final slides. I have actually left out a lot of interesting projects and the projects that are actually happening at MIT IBM now. These projects very often are more having a more computer science flavor and maybe less linear algebra there, but they all have something to do with graphs. So one project on the left here I'm showing is that we want to generate molecules. So the way we generate molecules is that we look at a molecule as a graph, and then we try to learn a grammar that can build piece of the graph, that can build a graph piece by piece. So first we generate a ring, and then get some branch, and then get another ring, and so on and so forth. So we need to figure out how to do that. I mean, so what is the grammar that can govern this process, so that this grammar can generate not only the original graph, the original molecules that we know, but we can also generate tons of molecules that we don't know. No one else in the world knows. And then chemists and material scientists can actually screen those newly generated molecules and figure out which ones are the ones that they need. Another project about graph, as I show here at the lower right corner, is about program translation. Actually, so this morning I mentioned to some of you, one of the projects that we are doing is to translate program among different languages, right? So if I have a MATLAB program, actually I want to have an AI model to translate it to Python for me, because maybe nowadays students don't know about MATLAB anymore, so they know only about Python. So they really desire some tool for doing that automatic translation. So one of the techniques we are using there is that we are representing a program by its parse tree. So when we compile a program, we generate a parse tree according to some grammar, and then we'll be encoding that parse tree into a vector, and then decode that vector back into another parse tree, into a parse tree in the target language. So that is one approach for us to do the translation. Yet another project is on the top right corner there, which is actually going back to the case how can we train graph neural networks for a very large graph. So we have done actually also quite a lot of system engineering in terms of doing, for example, if we have a cluster of machines, right? So and each machine has multiple GPUs, how can we do the training in a distributed multi-GPU manner? Or if we have the case of, I don't have any computing resources, I have only my laptop, then so we'll be doing some out-of-core computation because the graph itself cannot be fit into memory, and then all the data has to stay on the disk. So still, I mean, right, so then how do we do this training and so that we can also get the answer. So, right, so these are some additional projects that is actually happening actually now at the lab I'm at. And I think this concludes my presentation here. Please.
So I need to do a lot of reading, but you explain H versus O model. So explain again, once again, what is the difference between these two models that you propose?
The H versus O?
Yes.
Yeah.
And any guess why you're, yes, version one?
Right, so yeah, so let me repeat, right? So the question here is that, I mean, so why do we have two versions here and what is the difference? And maybe some of them is more useful than the other one in some occasions, but in what occasions, right? So in the H version here, right? So we are treating the W parameter in the graph neural network as the hidden state of a recurrent system. In the O version, we are treating that W as the input of that recurrent system. All right, so when we have a recurrent system, we always talk about two things. One thing is the input, and when a new input comes in, the system state evolves. Right, so that W could either be the state or be the input. So now comes to the question, which one would be more useful in what scenarios? So we hypothesize that when the input information is important, then treating the W as the input would be useful. Whereas if the input information is less important, but the graph structure is more important, then maybe just treating that as the hidden states of the recurrent system would be more beneficial. So there is one conceptual interpretation of why do we need two different versions when we use a recurrent system to evolve things. So the question here is that, right? So if I want to learn this graph structure, but if I do the optimization or do the training multiple different times, as we all know about optimization, right? So it depends on where we start. We eventually end up at a different location, right? So our model will be different. So does that mean that our learned graph structure will be different? That is actually a very good question. In practice, that always happens, and it is actually very hard to tell. In theory, what happens is that there is actually a very deep theoretical question about this kind of thing. So that is related to identifiability, right? So if I have some data, and if that data is actually coming out from a graph, some graph, can that graph be identified from the data, right? So this question is about the model itself. It's not about how we get that model, right? So assuming that we're actually doing the optimization perfectly, assuming the optimization have only one single optimum, and we always get to that single optimum with all these assumptions, and so then we started a question of identifiability. For this particular work, the answer is that we have not done the identifiability analysis yet. And that is actually a very good question. And if you are interested in, please help me.
check if there's any.
I don't think so. There is actually not a window here, so.